Hi, Science 10. So I marked your take-home exam. If you're unable to access your score, just let me know. So it's really good. Most of you are getting it in. There were a few of you who didn't manage to do that. Let's try to, it's a take-home open book exam. You should be able to get it done. If you're having some technology issues, just let me know and I can help you with that. So I want to go over the answers to the decay worksheet, half-life worksheet, and then we'll look at the final topic of the radiation short chapter here, which will be on fission fusion reactions. And then I'll give you a worksheet on that. And then on Thursday, I'll give you a take-home quiz on what we looked at so far with radiation. So we already went through the terms, so just a reminder, half-life has to do with how long it takes for half a radioactive material to decay. Decay curve shows the amount of material that's being lost, the parent isotope, over time. The parent isotope is the original isotope you start with that is going through the decay, and the daughter isotope is the isotope that is being produced as a result of the decay of the parent. So this table we had gone through last class. This was looking at things through a percentage. Here's looking at the same thing through a fraction, right? So as you can see, you just keep dividing by 2, and then the difference is going to be the fraction, the daughter isotope, right? So they all should add up to 1. Here's looking at it for number 3 in terms of mass, right? I think we went over that one. Okay, and so this was a decay curve for number 3. Okay, so now when you set up the decay curve, like here it said mass on the y-axis. Okay, so this is the y-axis, your vertical axis, and it said time on the x-axis, which is your horizontal axis. Now this A here, that's a symbol for years. Okay, so if you're wondering what the A represents. Now, this isn't the only way to set up a decay curve. You could set it up, instead of mass, you could use percentage or you could use fraction here. And then for the time, instead of time, you could also use number of half-lives. So for example, this would be 1 half-life, 2 half-lives, and so on. And so what you see, it's always going to have this type of shape. And so the parent isotope, which is what this represents, should always be dropping because you keep losing more of it. And what happens is after each half-life, so a half-life here happens to be 5 years, what happens is whatever you start with gets divided by 2, right? So 120, now it's 60, 60, then 30, 30, then 15, and so on. Okay, so that's what we mean by a decay curve. Here's another one with the mass of the parent isotope. So starting with 80 grams, and then every 20 years it drops by a factor of 2, divided by 2. And then here's your daughter isotope. Now let's look at the last one here. The ratio of the parent isotope to the daughter isotope after 2 half-lives. So what's happening, here's your parent, here's your daughter. So it's 20 to 60. So that means 20 parent to 60 daughter. And so when you do these type of ratios, you should always put that in lowest terms. Okay, so the correct way to put that is 1 to 3. Okay, and now here we're analyzing graphs. Okay, so it says use a decay curve. So there's, I think I did this one last time. So again, when you are wondering what the half-life is, look at what you start with and just go to half that, and then look at what time that corresponds to. Number 2, some of you are wondering which is the parent and which is the daughter. So again, the parent isotope should always be dropping, okay, and the daughter isotope should always be going up. And then the isotope pair, so when we talk about isotope pair, what we're talking about is the parent-daughter pair. So again, the parent is decaying to the daughter, so that would be potassium and argon. And then where they intersect, that's where you have equal amounts. So that means you have 50% of each. Okay? And same thing here with the ratio. Put that in lowest terms. Okay? Okay, so what we're gonna be looking at next is fission and fusion reactions. So I'll just kind of briefly talk about what the difference is between the two. So the word fission means to break apart. Okay, so think about if you had, say, like a let's say like a something like that was like a ball shape, and then it started fragmenting into different pieces. Okay, so that's what we mean by fission. And so the same applies here to what we looked at with the decay reactions, and that is the sum of the mass numbers doesn't change. Remember, the mass numbers are the numbers on the top, and the sum of the charges in the nucleus does not change, and then some of the atomic numbers on the bottom, number of protons, that shouldn't change. So here, what's happening is this is your big isotope here, uranium 235. This is N for neutron. Okay, what's happening is the neutron is kind of acting like a projectile. It's striking the large isotope of uranium 235, and then what it's doing is it's splitting it. Okay, and then these two are produced. So these are, in this case, you have multiple daughter isotopes. So this is produced from the breaking apart of the uranium 235. And then to find out what else is missing, we got to add up the numbers. So on the left here, the two add up to 236. 143 and 90 is 233. So that means we're 3 short, which means it's going to be 3 neutrons. So this is just like we did with balancing equations. You just put a coefficient in front, and then here you got 92 plus 0, so that's 92. 54 plus 38 is 92. Therefore, this has to be 0. Okay, so that's called a fission reaction, is when you have a large isotope that gets split into smaller isotopes, but they're still considerable in size. The opposite of that type of reaction is a fusion reaction. A fusion reaction is where you have very light isotopes. Fuse means combine, and then the same idea. You're just trying to make the numbers match up. These type of reactions are significant. Fission reactions are what we use in nuclear reactors. So the byproduct of this is going to be a considerable amount of energy. Right, so that's kind of the point of the reaction. And these 3 neutrons that are produced, they're going to target more of the U-235 that's available. And so this is what we call a chain reaction. Okay, so a chain reaction, it's a fission that produces subsequent fission reactions, and then you have a controlled chain reaction so that you keep getting an energy output. Okay, so that's from a nuclear fission reactor. The other application here would be a nuclear weapon of some kind, where you have something like U-235 in a container that gets bombarded by neutrons, and that detonates into a large explosion. So that would be an example of an uncontrolled chain reaction. The same idea would happen in a meltdown of a nuclear power plant. A fusion reaction also is going to produce a considerable amount of energy, and this is the type of reaction that is used to power stars, right? So the reason why we know a star's life is finite is because at some point you're going to run out of the small nuclei that you start with on the reactant side. So it's almost like the star runs out of gas, right? And that's where it starts going supernova. But that takes a considerable amount of time before that happens. The fusion reaction, this is something that we do not have the technology to do this type of reaction in a reactor type setting, because in order for this reaction to occur, you need it in an environment that has a lot of heat, right? So that's why you hear the term cold fusion. Cold fusion is a theoretical concept where you could get a fusion reaction to occur at a lower temperature, but that hasn't been discovered yet. Okay, so both of these reactions, what they have in common is they produce a large amount of energy. They're kind of mirror opposites of each other. The fission reaction is where you have a large nuclei that get split. A fusion reaction is where you have light nuclei that combine together. Okay, so these are examples of nuclear reactions, but the same idea behind these reactions are in what we did in the decay reactions. Okay, so I'll have you go through this worksheet on fission and fusion, and then I'll on Thursday's class I'll go through the answers to this worksheet, and then I'll give you the take-home quiz to do. Okay, so let me know if you have any questions. Again, let me know if you're unable to find out what your test mark is, and I can help you with that. Okay, so again, stay safe, and I'll talk to you again on Thursday. Okay, bye now.